Hey, welcome to the video for the paper Meta-Learning State-Based Eligibility Traces for More Sample-Efficient Policy Evaluation. Brought to you by McGill University, Mila, the Quebec AI Institute, and DeepMind. So, what problem does this paper seek to address? It is the universal problem of the hyperparameter tuning for trace-based policy evaluation methods. For example, TD lambda, gradient TD lambda, or shortly GTD lambda, etc. In general, the methods are very sensitive to the values of the hyperparameter lambda when applied on all sorts of different environments. Thus, RL practitioners mainly use grid search or random search to get better lambdas, essentially rerunning the algorithm lots of times. In this paper, we seek the possibility of using a meta-learning method, which means that the method will automatically adapt lambda during the run to solve the issue. The following contents may require familiarity with the general trace-based policy evaluation methods and notions like lambda return, state-based lambda return, etc. The contribution of this paper is Meta, a plugin for trace-based policy evaluation methods, which we will also refer to as the baselines. This plugin collects the auxiliary information from agent-environment interactions and assists the baseline by providing a lambda value per update. The reason why we recognize Meta as a plugin is that it has minimal influence on the behaviors of the baselines, and it is compatible to nearly every learning setting. It works both online and offline, both in the tabular case or with function approximation. It is compatible with off-policy learning and even can be used for assisting control methods by making the policy evaluation more sample efficient. So let's see intuitively how this plugin works. On the left-hand side, we have a baseline, which can be any trace-based policy evaluation method. The agent selects action given some policy, and the environment returns the reward, observation, and optionally discount. The update to the value function is conducted with the reference to the preset value of lambda, which is fixed and the same across every state. On the right-hand side, we have the exact same baseline, but with Meta plugged in. We spot the difference of auxiliary learners, which are colored in purple, which also uses the reward, observation, and discount returned from the environment. Also, the fixed lambda is replaced by observation-based lambda, which is essentially a per-step lambda value suggested by the plugin. Given the fact that the plugin needs no additional information that the baseline needs to function, we can clearly see the potential of the method being applied pervasively. We would also like to mention that this framework of using auxiliary tasks to help the baseline was first proposed in White and White 2016. We developed our method under the same mindset. Well, beyond the intuitions, Meta is actually a principled method that was derived for improving the sample efficiency. First and foremost, the key idea of this paper is to improve the sample efficiency by improving the quality of the update targets. TD update at the very core is to construct an update target and then move the current value estimate towards the target according to some step size. The update target, as we can observe, is a random variable. We can view this as if the value learner is chasing towards a random target. Better constructed update targets yield significantly more effective updates and therefore boost sample efficiency. The ideas of improving the update target, though via different means for different purposes, have existed long before this paper. For example, the target network in DQN is used to stabilize the update targets for better TD updates. The update targets are per state and per interaction, when it is online, of course. Thus, the adaptation of the update targets require per state degrees of freedom, which point us to per state lambdas, which we call state-based lambdas. We know that TD lambda with state-based lambdas has very well-defined fixed points. This means our adaptation, if successfully discovered, will not affect the convergence of the convergent baselines themselves. The adaptation of lambda, as we show in proposition 1, requires auxiliary information, which can be estimated using the trace-based auxiliary workers in the online setting, and many other types of methods in the offline setting. The main contributions of this paper are mainly three. The first is a theorem showing per state update target improvement, if properly weighted, can result in an overall update target improvement, which leads to better overall sample efficiency. The second is a proposition that derives an approximation to improving the per state update targets. The third contribution is the way of assembling the theorem and the proposition together. To conduct the per state updates, we need auxiliary estimates of the statistics of the update targets. However, the interdependencies of the state update targets and the state lambdas cause trouble when doing the adaptation. We address such a problem using trust region style updates. Here we provide more insights into the paper. First, the meta updates change the state-based lambdas continuously with some very small step size. This means the quality of the update targets is chasing the optimality all the time. The continuous changes of lambdas also change the optimization landscape. Therefore, there is no guarantee that the algorithm is surely optimal. Second, the auxiliary information needed for the meta updates, which is estimated using the auxiliary learners, should be set up carefully in reality. The tricks include using higher learning rates for the auxiliary learners than the value learner itself, as well as using buffer periods, during which no adaptation is conducted to stabilize the auxiliary estimates. Third, meta knocks out the tuning of lambda by introducing another tunable parameter kappa, which is the step size of the meta updates. This seems disappointing. However, we should point out that there are several benefits. The first is that by this exchange, we used just one kappa to enable different lambdas for every state, therefore unlocking significantly more degrees of freedom for optimizing towards sample efficiency. Second, from the experiments, we got very strong intuitions for choosing the value of kappa. As long as it is small enough, the performance would be good. Here we have come to the experiments. The experimental section of this paper mainly focuses on validating the effectiveness of the contributed method, meta, under diverse test settings. For policy evaluation, we test the compatibility of meta with off-policy learning, functional approximation, in lower variance and higher variance environments. For our control, we test whether meta could contribute to the sample efficiency in policy gradient-based agents. In the following sets of experiments, we always compare the performance of the baseline, the lambda greedy assisted baseline, from White and White 2016, as well as meta-assisted baseline. As discussed before, a baseline method with meta plugged in tunes the hyperparameter kappa instead of lambda, while lambda greedy eliminates the hyperparameter tuning for lambda. We use the classical U-shaped curve visualization for displaying the differences in the performance of the methods. The first set of experiments is featured on a tabular environment, namely ring world. In this environment, the states are connected as a ring. Only a left or right action could make the agent travel to the left or right adjacent states. The agent always starts at the top of the ring, and the bottom two states of the ring are terminal states with -1 and +1 rewards, respectively. There are no more stochasticity. We use baseline true online TD lambda in this set of experiments with a pair of behavior target policies to enable off-policy learning. In the diagram we show here, the x-axis represents the learning rate of the TD updates, and the y-axis represents the weighted error between the final value estimate and the ground truth, which is obtained using dynamic programming. As we can see with nearly every learning rate, the meta-assisted method consistently achieved the best performance among all. Comparing the lowest points of the baseline curves across different learning rates and the M-star curve, we can see that tuning kappa can indeed bring more potentials to the performance, as we have claimed. The second set of experiments is featured on a high-variance environment called Frozen Lake. In this environment, the agent tries to get to the southeast grid from the northwest grid while not falling into the holes on the frozen lake surface, using the unit directional moves. The slippery surface brings random repeat and momentum into the moves, making the task significantly more stochastic than ring world. For feature construction, to simulate non-tabular states, we use discrete variant of tile coding to form overlapping tiles and enabled linear functional approximator with the baseline method true online GTD lambda. In this experiment, we see the same patterns as in the first set of experiments. Additionally, since the state feature constructions for the value learner and the parametric lambda do not necessarily have to be the same, we used one-hot encoding on the parametric lambda to get a non-parametric version, which corresponds to the legend M star NP. As we can see from the U-shaped curves, parametrizing lambda brings performance gains, and this says that the parametric lambda could be very beneficial for they utilize the power of generalization. This also means we can make lambda a neural net to unleash more potential to the setting. The very last set of experiments is very different from the first two. This is for the control case. We test the linear actor critic with softmax policy on mountain car, a classic control environment in which the agent tries to move the car towards the flag on the top of the mountain, and each move yields -1 reward. Here we can see that the performance gain is not as significant as those we have seen in the first two sets. We think it's because improving the sample efficiency of the policy evaluation inside a control agent does not necessarily mean that it will improve the policies faster. This is a way more complicated issue to address. And thank you, that's all. For more discussion, more information, please contact us at my email address right here. The implementation, which is written in Python and NumPy, is available at the URL right here. See you, and we wish you all the very best.